All right, thank you, Jennifer. And I thank Hearts for inviting me to speak today. Hopefully what I have to show you will be informative. I've been invited to speak on some of our enhanced proppant technology that we've just developed that really has been developed to not only enhance production, but really more importantly to decrease costs. What I'll do is I'll just give a very brief introduction of the technology, talk a little bit about the technology enablers. You know, what is it that we've done to allow us to enable these proppants to be used for things other than propping. We'll then work in some field applications. I'll talk a little bit about some things we've done in the Permian and then quickly summarize. So when you think of proppants, or proppant, what we typically think of is, of course, sand, resin-coated sand, and ceramic. And you know, proppant, of course, has been around as long as there's been hydraulic fracturing, for over 70 years. And primarily its purpose has been and still is to prop open rock. We know if we don't place proppant, generally speaking, into our fractures that we won't produce hydrocarbons. However, over the course of the last several years, we've started developing some technologies because really, if you think about what proppant technologies have been focused on before, it's been on that conductivity emplacement. So whether it's going to a man-made ceramic or putting a resin on for flowback control or perhaps using detectable technologies, things like that. What we've primarily done as an industry is just key on, you know, how do I make proppant better or more functional for replacing conductivity. But the question then remains, if you think about what's happened over the last 10 years, we used to hydraulically fracture only about 10% of our wells, whereas now it's completely opposite. We're putting proppant in almost every well we drill. So the question is, can we do something else with that proppant while it's also performing that same function? If we look at what happens in a typical reservoir, after we complete and frack the well, we bring it on production, and we begin to have, in many cases, production issues. Some of those are things that we've done, whether it's gel damage or bacteria or overgrowth, or it might be something that just occurs as we begin to produce the well. Paraffins, asphaltenes, scaling, things like that. And of course, the problem we have in horizontal wells with multi-stage fractures is once you have that problem in the fracture, it's very difficult to remediate because we don't have really, unless we spend a lot of money trying to focus chemicals or things into those fractures, it's just kind of a pump and pray kind of thing. So what we thought was, well, look, we're putting proppant in here already. What can we do to the proppant to help deploy these chemicals? So that's really what led us to this technology, and the technology is basically to utilize the proppant that we're already placing into the reservoir to deploy these inhibition type chemicals. If you think about it in the human body, what we're trying to do is we're basically trying to inoculate the well from the fracture tip all the way to the production facility. Once you've inhibited it, carries it through the system. What this allows us to do then is prevents us from having to handle all the solids associated with scales and paraffins and wax. It also allows us to reduce the environmental impact at the surface. You don't have to handle all the chemicals associated with it. And then, of course, the other side of that is the production losses. And many times we probably don't realize we're getting the production losses. And like I said before, there's something that we can prevent having to do expensive remediation. So let me talk just a little bit about what are the technology enablers for this technology. When we make a ceramic proppant grain, you basically take raw materials, you pelletize it, make pellets, and then you sinter it. Our goal typically to make a high quality proppant is to reduce the internal porosity. Most proppants are going to have 3 to 5% internal porosity just due to the manufacturing. However, we can engineer porosity into that pellet if we choose to. So that's what we're doing with this technology. We actually, during the process, purposely put porosity into the proppant grain. That porosity is spread out through the entire grain, and it's interconnected. So that does a couple of things. By spreading it out through the grain, it at least maximizes the strength of that pellet for that amount of porosity. But the other part is that it allows us to put a tremendous amount of chemical by weight into that those proppant grains. Because of the fact that it's interconnected porosity. So what you see there on the chart is basically a cross-section of a ceramic proppant pellet that has porosity. The red, which is probably kind of hard to see in the back, but the red is basically scale inhibitor that's inside of all the internal porosity. So it's completely spread out throughout the grain. So that in and of itself is kind of the previous technology, and that allows us to place chemicals. However, what it doesn't do is it doesn't slow any type of an elution rate. So what we also then have done is we add an outer membrane, a semi-permeable membrane. We can engineer that membrane to have small or large pores depending on what we're infusing into the pellet. But what that does, that's the critical component of this technology, because what it does is it allows us to slow that elution rate. Previous technologies of this sort, when you pumped it into the well, it very quickly eluted and came off, and so it was a very short-lived application. But now what we're seeing is, after multiple years, we still have 70 or 80% of the chemical still in the frac or the pack. So it has substantially slowed the elution time. So if we kind of go to what we call our guard technologies, that's really the employment of this technology. What we're going to do is we're going to tailor it to a specific well or to your application. So it's going to depend on water chemistry or oil chemistry or whatever it is we're trying to inhibit. It's typically going to replace about 5 or less than 5% of the proppant pack. And really a lot of that just depends on how much proppant you're putting in the well. What we're going to do is we're going to come in and say you need to pump 30,000 pounds, and whatever percent that is of your total proppant is what that is. But it replaces the existing proppant with this less than 5%. We're going to blend it on site, or we're going to blend it ahead of time and bring it out to location ready to go. And most of these chemicals then are set up such that they just treat the fluids you want to inhibit. So, for example, if it's a scale inhibitor, it's only going to elute when water comes in contact with that grain, not hydrocarbons. It says, we typically talk in terms of years, but really we're inhibiting barrels of water or barrels of oil. So it really just depends on flow rates as far as how long those things last. And again, what you're going to see is that this technology really pretty much pays for itself immediately because of the reduction in lease operating costs. If we look and go to scale guard specific, so this is the scale inhibitor technology, we can either put a DTPMP, a base phosphonate inhibitor, or a polymer base inhibitor in. We're going to blend it typically at less than 1%. I have 20% on there. We have done some work in the Gulf of Mexico where we put 20% in there because they're smaller fracs. We're going to monitor those residuals and continue to look at how the elution profiles occurred. And what we're finding is that some of our oldest installations, they're still scale-free after over 2 years. Here's just one example. The first installation we really primarily did that we got a lot of good data on was in the Uinta Basin. You can see there were 15 wells or 20 wells in this trial. 15 of them used the scale guard and 5 of them used another particulate-based inhibitor. You can see the black line represents that offset inhibitor, and it really essentially after 140 days was gone because there's no coating on that, and again, it's not a proppant. You can see that there is initial wash-off on the red line. That would be the scale guard. And then after that, it very quickly drops to a minimum inhibition concentration. So in this case, this well needs about 5 ppm in order to inhibit scale, and we're basically rocking along there at about 7. And this well is now over 700 days old, still getting residuals back, and at this point in time, we've produced about 30% of the scale inhibitor. So we still have many, many more barrels left to inhibit here. We've got field applications all over North America, essentially at this point. Most of those in the unconventionals, the center, the land-based, are, again, less than 1% applications, just kind of your typical scaling that's occurring because of the frac waters that we put in. I'll point out Alaska. Alaska's kind of unique. We put a 5% in there, and the deal there is they're waiting for water flood breakthrough. So that chemical sitting there dormant in the grains until they get the breakthrough, because when breakthrough occurs, they get a huge amount of barium sulfate scale deposition, and so you can't predict exactly when that's going to occur, so they need to have the inhibition work in place. And in the Gulf of Mexico, that's an offshore well, a couple of wells where we've actually loaded up to 20%. In that case, it's going to inhibit about 10 to 15 million barrels of water over the course of its life. And again, we have everything kind of in between. Been in the Bakken, the Rockies, Permian. If we kind of move to Permian specific, I just have a one-slide summary for what we've done there. Primarily what we're finding is we're targeting barium and calcium. We've treated anywhere from low rate to high water rate wells. Most of the big horizons there, you got Avalon, Sprayberry, Wolfcamp, Bone Springs. We've got the first installation's been in place for about a year. So far it's working very well. We had an operator contact us it's been about a month now, who typically has to pull their tubing string to install a submersible pump after a certain amount of time, and usually they expect to see scale at the end of that tubing, and they said this is the cleanest they've ever seen it. So it's working very well. That was an Avalon installation. And so what we're finding is it's really having the opportunity to replace both your liquid inhibitor during the frac, as well as surface installations, and then any other type of inhibitor that was being used. So that was ScaleGuard. We also have some other products that we have been working as well. ParaGuard, which is a paraffin control. The way that technology works is that's going to lower the pour point several degrees of your crude. It's basically 3 classes of modifiers all in one into that. So what we're trying to do is we're trying to inhibit a broad spectrum of waxes. And so that's in place. We've already developed that product, and we're about to place that into its first installations here in the next month. I think that one will have application out in the Permian. We also have an H2S guard. H2S is kind of an interesting thing. How do you inhibit H2S? And a lot of what's being done with chemicals at the surface is it's really keyed on residence time. You need to have those fluids in that chemical for as long as possible. And so by placing it in the fracture, it has quite a bit of residence time, so we think that it's going to have a pretty big impact. There again, that product is in development as well, and we expect in the next couple of months to have the first installation of H2S guard. And then Salt Guard, probably not as big a Permian application. It's really more of a Bakken application. That was actually the second product that we developed after Scale. We have placed that in several wells in the Bakken. What that product does, it actually modifies the crystal, so it doesn't tie up like a scale inhibitor is going to tie up the barium and the calcium or the ions. This one is actually just going to, the salts still form, but it modifies the crystal structure so that it just flows out of the well and doesn't attach. Those are kind of the 3 primary in development products or about to be commercial. We also are working on some other products as well. So we've had a request for asphaltene work. We've had requests for corrosion. We've actually dabbled a little bit in gel breaker, although that's kind of a crowded space. And then the other thing we've actually tried to use this technology for, it's completely off topic for a guard product, and that is to perhaps put a tracer in there. Perhaps an oil or a water-soluble tracers, gas-soluble, to be able to start looking at production logging type applications. So that one's kind of on the horizon for us. We haven't quite got there yet on that. We're trying to, of course, got limited capital, and so we're trying to focus on what we think is the quickest to market. So let me just kind of summarize the talk. We've, like I said before, proppants, generally speaking, we think of as, deploying connectivity into your fracture. And what we've done is we've developed a way to take that proppant, and in addition to propping a fracture, also deploy chemicals in a very efficient manner. Again, think of it as inoculating your production stream, your production system against these bad actors. And what we're finding is that we can decrease lease operating costs dramatically. That's the only thing kind of got to work on is you're going to move capital AFE money over to lease operating or back and forth. So that's the only kind of thing you got to work through there, depending on which side of the fence you sit on at your company. But what we are seeing is that really it pretty much pays for itself as soon as very quickly after we place it. And with that, I will turn it back.